Hey folks, welcome back, and we are going to continue our discussion of the limit equilibrium method, and we'll look at some more advanced techniques. Before we dig in too deeply, let's talk about the general method of slices. As you may recall, with the method of slices, we subdivide the moving mass of the slope into a series of vertical slices, and then we analyze the forces on those slices, and by doing this we can come up with a factor of safety for the slope as a whole. And so on the left we have the general free body diagram of a slice. It has a width delta x. We sometimes refer to that as b. The slice itself has a mass w, the weight, which operates through the center of mass. And then on the base of the slice, which is a width L, we have the shear force, capital S, the normal force N. The shear force is a function of the effective strength, the pore pressure, the normal force, the factor of safety, and the width of the base of the slice, delta L. The factor of safety comes into play because the actual shear stress along the bottom is represented as the mobilized shear strength, so the shear strength divided by the factor of safety. And then on the sides we have the normal forces E, EI on the left, EI plus 1 on the right, and then we have the shear forces XI and XI plus 1. So as we look at this, looking at our unknowns, assuming we have n slices, and we're talking about the lowercase n, the unknowns are one factor of safety, n values of n, the normal force, n locations for n, meaning where does n act on the base of the slice, n minus 1 values of the side force E. It's n minus 1 because if we have n slices, we have n minus 1 boundaries between the slices. And then n minus 1 values of E, and then n minus 1 locations for E. At what height along that side does the side force E activate or act? So we add those up, we get a total of 5n minus 2 unknowns. And then we have 3n equilibrium equations. For each slice, we can sum the forces in the vertical direction, sum the forces in the horizontal direction, and we can sum the moments. And if you look at this, we have 5n minus 2 unknowns and only 3n equations. More unknowns than equations means that unless we make some simplifying assumptions, this is statically indeterminate. And so as we look at the different methods today, they each differ in terms of the simplifying assumptions they make to reduce the number of unknowns, and then the number of equilibrium equations that are satisfied. By the way, as we look at the side forces, we had the X and E normal force and shear force. Instead of representing that as two forces, you can do a single resultant force P acting at an angle theta. But in either case, we have two unknowns on each side. We can do X and E, or we can do P and theta. But we end up with the same number of equations and unknowns. And in the slides we'll look at today, we'll do it both of these different ways of representing the side forces. So, in summary, we're going to look at a number of techniques that are based on this approach. Each one uses a different set of assumptions. If they only make 2n minus 2 assumptions, then they can solve all 3n equilibrium equations, in which case we call it a complete equilibrium method. And if we make greater than 2n minus 2 assumptions, that we will satisfy less than 3n equations, and this is a partial equilibrium method, and we'll look at both of these. So the first one we're going to look at is the simplest. It is called the ordinary method of slices. The ordinary method of slices, the key assumption is the side forces can be neglected, or you can think that they sum to 0 on each slice. Same magnitude, same location. And therefore, our free body diagram is a lot simpler. We just have W, S, and N. And if we sum forces perpendicular to the base of the slice, so in the direction of N, N is equal to W times the cosine of alpha, where alpha is the angle of this slope, but also it would be the angle that W deviates from the direction perpendicular to the base of the slice. And so the normal stress would be N divided by delta L, or W cosine alpha divided by delta L. So if we go back to our general equation, now for the factor of safety, now remember this equation came from summing moments about the center of the circle. And the numerator on the top are the forces or the moments driving, or excuse me, keeping the slope in place. So that would be the shear strength acting on the length across each slice, and it would be divided by the forces driving failure, which for each slice would be W sine alpha. There was another term, the radius of the circle, but that is on the numerator and the denominator, so it cancels out. So it's basically the sum of the forces resisting failure divided by the sum of the forces driving failure. And if we substitute this expression up here for sigma into this equation and simplify it, we get this equation for the factor of safety. So that's basically the total stress analysis form of the factor of safety for the ordinary method of slices. And if phi is equal to 0, then that right part of the numerator cancels out, and we're left with this equation, sum of C delta L over the sum of W sine alpha, which is the same solution we found earlier for the generalized method, or the Swedish method of slices. Okay, for an effective stress analysis, we plug in C prime, phi prime, and sigma prime, the effective stress, and the effective stress is equal to the total stress, W cosine alpha over delta L, but now we subtract the pore water pressure U. So if you plug this expression into right here for the effective stress, and then simplify the equation, we get this equation for the factor of safety for effective stress conditions. Now, the problem with this form of the equation is over on the right side of the slope, where that slope angle at the bottom, alpha, gets large, then the cosine of alpha gets small. So this term gets smaller and smaller, while this stays large, assuming there are pore pressures on that side. In which case you could end up where this minus U delta L is larger than W cosine alpha, and you're counting on, basically, you have negative effective shear stress, which you're counting on tension, which doesn't really happen in soils. And so it's unconservative. It gives you a factor of safety that's higher than it should be. To account for this, we have an alternative formulation where we come up with this vertical effective unit weight, represented as W prime. It's equal to the weight of the soil minus the pore pressure times the width of the X width of the slice along the bottom. And then if we sum forces perpendicular to the base, we can say N prime is equal to W prime cosine alpha, and substitute in W minus UB, and B is equal to delta L cosine alpha, and we end up with this expression for N prime, the effective normal force. And if we then take that effective normal force and divide by delta L to get the effective stress, we come up with this alternative formulation of the effective stress, which is the same as what we had before, but now we have this cosine squared alpha term on the U. And if we plug that into the equation, this becomes our new equation for the factor of safety. And let me back up a little bit. So this this is, whoops, let me go back. This is what I wanted to compare it to. So this is the factor of safety for effective stress conditions. The original one, we have minus U delta L, and here we have minus U delta L cosine squared alpha. The effect of that is when that alpha gets large, cosine squared alpha gets small, and it reduces the impact of the pore pressure, and so it's much less likely that you get negative effective stress. And so it's a more conservative approach, and so this is the preferred formulation for the ordinary method of slices. So, summary, ordinary method of slices, it's based on a circular shear surface. We're summing moments around the center of the circle. It only satisfies moment equilibrium. We do not satisfy force equilibrium. And for phi equals 0, we get the same solution as we got with the Swedish method. The factor of safety does not require any iteration as opposed to most of the rest of the methods that we'll look at today or in these lectures. And it's the simplest but perhaps the least accurate of the other procedures of slices.